Imagine walking past something really mundane, something you see every day, like a concrete pillar, maybe a sidewalk. Now, what if that same concrete suddenly had, well, superpowers? Imagine it being, say, 16 times stronger, 300 times more ductile, and almost totally impermeable.
Mm,
Okay, so that sounds maybe, but it's actually the potential of something called ultra high performance concrete, UHPC.
exactly. And that's what we're diving into today. We're drawing mainly on a really comprehensive review article from the Construction and Building Materials Journal.
Mm.
Our plan is basically to unpack what makes UHPC tick,
Yeah.
where it's being used, what's holding it back, the challenges, and maybe peek into its future a bit.
And why should you care about this? Well, think about the world around you. Those bridges you drive over, tunnels, the buildings that make up our cities. UHPC could genuinely change how we build all that critical stuff. Make
Right.
it, way stronger, last incredibly longer, maybe even more sustainable in the long run.
Right.
So, what is this stuff? How is it so different from the regular concrete we see everywhere?
Well, fundamentally, it's an advanced composite. It's a very carefully designed mix of cementitious materials and fibers. The big differences compared to standard concrete. Okay, first, a really, really low water-to-cement ratio. We're talking like 1.5 to 0.25.
Okay, wait. 0.15. Normal concrete is more like 0.4 or 0.5.
Exactly.
No.
Much higher. So with UHPC, you need these powerful chemicals called superplasticizers just to make the mix workable, to make it flow. They sort of act like tiny ball bearings between the particles.
Oh, okay. So you need chemical help just to mix it because there's so little water.
Pretty much. And the other major thing, no coarse aggregate. None of those little stones or gravel bigger than, say, 5 millimeters. Instead, it uses very fine sand, a crucial ingredient called silica fume, which is this incredibly fine powder, a byproduct for making silicon.
Silica fume, right. I've heard of that. So not just fine sand, it's this specific industrial material.
Correct. And very often steel fibers mixed throughout the whole thing.
Steel fibers. Okay.
And all of that, the specific recipe, the mixing, the curing it, leads to this microstructure that's just incredibly dense, homogeneous. The pores are microscopic,
Yeah.
way smaller than in normal concrete.
And that structure, that density in the tiny pores, that sounds like where the superpowers come from.
That's exactly it.
Yeah.
That tightly packed structure is why it has these, well, extraordinary properties.
Okay, let's talk properties then. What kind of numbers make it stand out so much?
Strength is probably the headline. Compressive strength, often over 200 MPa.
200. Wow. And normal concrete is.
Typical stuff for buildings, bridges, maybe 20 to 42 MPas. So yeah, UHPC can be anywhere from 3 to like 16 times stronger in compression.
That's a huge leap.
And its tensile strength, its ability to resist being pulled apart, is also way better, often above 20 MPa. Normal concrete is famously weak in tension.
Okay, so the strength is massive. But what about durability? Concrete degrades, right? Cracks, corrosion.
Well, this is where that dense, low-porosity structure really shines.
Yeah.
It makes the material basically impermeable. Water, aggressive gases, chlorides from de-icing salts, they just can't get in easily.
I see.
So that translates to amazing resistance against freeze-thaw cycles, chemical attacks, corrosion of any steel inside. It just lasts. Much, much longer service life, far less need for maintenance.
Less fixing, less replacing. So that's a huge deal for infrastructure, obviously. What about impacts? Or how it behaves under, extreme stress? Does it just shatter?
No, and that's the other key difference. Ductility and toughness. Unlike regular concrete, which is brittle and just snaps under tension, UHPC, especially with those fibers, it shows significant strain hardening. That means even after it starts to microcrack, it can actually carry more load before eventually failing.
Strain hardening. Okay.
The review article we looked at mentions it has something like 300 times the ductility and energy absorption of even high-performance concrete.
Wait, hang on. 300 times? That sounds almost unbelievable. What does that mean practically?
Well, think about earthquake zones. That ability to absorb energy, to deform quite a lot before failure, that's critical.
Right.
It means a UHPC element might bend or sway significantly under forces that would just shatter a traditional concrete one. It's a game changer for resilience against things like earthquakes or even blast loads.
Wow. Okay, so it's not just stronger, it fundamentally behaves differently under stress. It fails, or rather resists failure in a completely different way. So with properties like these, where is this stuff actually being used today?
Well, those properties translate directly into design benefits. You can use less material, right? So elements can be smaller, thinner. That means lighter structures, maybe more elegant designs, new aesthetic options.
Yeah.
Bridges are a huge area. We're seeing it used for bridge decks, for the main girders, for the joints between segments, as overlays to fix older bridges, even entire bridges built segment by segment using UHPC.
Why bridges specifically? What's the big advantage there?
Well, the strength lets you design longer spans, more slender structures, fewer piers maybe, and the durability is massive for bridges, especially less maintenance over decades saves a fortune.
Right, the long-term costs.
Yeah. The article mentions a few key examples, like the Wapello County Mars Hill Bridge in Iowa. That was the first U.S. road bridge made with UHPC back in 2006. And the Tokyo International Airport Bridge in 2008, world's longest segmental UHPC road bridge at the time. And some pedestrian bridges, like the Sakata Mirai in Japan, really show off the aesthetic side. It's got this cool perforated mesh look because UHPC can be molded so well.
It really sounds like it opens up new possibilities, not just better performance, but different kinds of structures altogether.
Absolutely. And beyond bridges, you see it in buildings too. There's complex architectural designs. Anywhere that high strength-to-weight ratio or its ability to be cast into complex shapes is useful. Think architectural cladding. The article mentions the Qatar National Museum, the Fondation Louis Vuitton in Paris. Really intricate stuff.
Okay. What about other big infrastructure, like power plants or tunnels?
Yeah, it's finding niches. Wind turbine towers. You can make them taller and more slender with UHPC. Tunnels, thinner linings mean more usable space inside for the same excavation effort. Its properties are also good for things like nuclear facilities, better radiation shielding, blast resistance, and for offshore structures, that durability in harsh marine environments is a big plus.
And you mentioned fixing older structures, rehabilitation.
Yes, is proving really effective there. You can apply a relatively thin layer of UHPC as an overlay on, say, an old bridge deck, like the Limoges River Bridge in Switzerland example. That overlay dramatically boosts the strength and durability, extending the life of the existing structure.
And the ductility helps in earthquake zones, you said?
Exactly. That energy absorption is key. Sometimes you see it used in specific parts of the structure, maybe hybrid elements combined with normal concrete, or in things like foundation piles, where it needs to resist high impacts during driving.
Okay, so we've got this picture of a material. Well, almost too good to be true. Incredible properties, really useful applications. But if it's that good, why isn't it everywhere? There has to be a catch, right?
Oh, there definitely are catches. Significant hurdles. The review article is very clear about this. And the biggest one, by far, is cost.
Right. How much are we talking?
Well, Well, proprietary UHPC mixes, they can cost maybe $2,500, even $3,000 per cubic meter.
Wow. And standard concrete is?
Around $170 per cubic meter.
Whoa. Okay, yeah. That's a massive difference. Why so expensive?
Well, about half of that cost is just the raw materials. Those special steel fibers, the superfine silica fume, high-quality fine sand, they cost a lot more than the simple gravel and standard cement in regular concrete.
Okay.
Plus, UHPC uses a lot of cement per cubic meter, sometimes double what normal concrete uses. And ironically, a fair bit of that expensive cement doesn't even fully hydrate. It just acts as a very expensive, basically.
So pricey ingredients and lots of them. What about actually making it and using it?
Yeah, that's another challenge. The production is complex. Because it's so stiff, that low water content, again, you need specialized high-energy mixers. Scaling that up for really big pours on a construction site can be difficult with the current equipment we have available. And just managing all the different components precisely takes care.
So mixing and placing it is tricky. What about designing with it? Are the rules different?
They are, and that's another hurdle. Compared to traditional concrete, UHPC is still relatively new. So there aren't universally agreed upon design standards everywhere. Predicting exactly how it will behave long-term, especially once tiny cracks might form, still needs more research and data. The specific ways you need to batch it, mix it, cure it, they're different. And critically, there just aren't that many engineers, contractors, or workers yet who have deep hands-on experience with using it on a large scale.
So a knowledge gap, an experience gap.
Exactly, that more widely through the industry. Fewer companies really have the expertise for big projects right now.
Are there other technical question marks hanging over it?
Well, yeah. While the fibers make it ductile overall, the basic cement matrix itself is still brittle. And researchers are still looking closely at the very long-term durability after microcracking starts under load. And on the sustainability side, sometimes ensuring you can get consistent quality and supply of those supplementary cementitious materials, the SCMs like fly ash, can be a challenge depending on the region and source.
It definitely sounds like there's still work to do research-wise to make it more mainstream. What specific areas does the review highlight for R&D?
Yeah, several key things. One big one is standardizing testing methods and material requirements globally, just getting everyone on the same page. Optimizing the mix designs is crucial. Finding ways to get the performance needed, but maybe at a lower cost. Could we use fewer steel fibers, more fine aggregate, maybe more locally sourced materials? Definitely. Developing those unified design standards we talked about is essential for engineers to feel comfortable using it more widely. And researchers are looking at alternative curing methods, ones that maybe need less energy than the heat curing often used now.
Okay.
And then there's the more futuristic stuff. Using UHPC in 3D printing, which has its own challenge, pumpable and figuring out reinforcement,
Yeah.
or even making it smart, self-sensing concrete. But then you need to know how things like moisture or temperature affect those sensing properties over decades.
Let's circle back to something we touched on, which really feels like a bit of a paradox.
Yeah.
Sustainability. We know cement production is a huge CO2 emitter. UHPC uses loads of cement. How does that balance out?
Yeah, that's a really critical question. And you're right. Cement production is responsible for what, up to 8% of global CO2 emissions?
Yeah.
It's significant.
Mm.
And UHPC does have a very high cement content per cubic meter, like you said, often double that of standard concrete, maybe around 1,000 kilograms versus less than 400.
So yeah, on the face of it, it looks worse for the climate, doesn't it?
It does seem that way initially. But here's the nuance that the article really brings out.
Yeah.
Because UHPC is so much stronger and more durable, you need way less of it to do the same job. Take a structural column, for example. A UHPC column might only need, say, 44% of the volume of material compared to a conventional concrete one designed for the same load.
Ah, okay. So it's about efficiency in the structure, not just the mix itself.
Exactly. So the total amount of cement used in the finished bridge girder or column might actually end up being similar, or potentially even less, than the conventional design, despite the richer mix.
Interesting.
And then you add in the durability factor. A UHPC structure might last 100 years or more, with drastically less maintenance needed compared to a traditional one.
Right. The life cycle.
Think about all the emissions saved over decades by not having to do frequent repairs, replacements, less transport, less energy used for maintenance. That massively reduces the overall lifetime environmental impact.
So the long view completely changes the equation. Less maintenance equals lower lifetime impact.
Definitely. And the source also mentions that because not all the cement in UHPC fully reacts, there's potential for it to be recycled quite effectively, maybe multiple times. Another plus for circularity.
And you mentioned carbon capture potential. How does that work with a cement-heavy material? Seems counterintuitive.
It is fascinating, isn't it? Normally, carbonation CO2 reacting with concrete is a degradation process, but researchers are looking at ways to actually use UHPC's dense structure to capture CO2, things like CO2 curing during production. Plus, using those SCM supplementary cementitious materials like GGBS, that granulated blast furnace slag.
Yeah, the industrial byproduct.
Right. Using those can actually enhance the amount of CO2 the concrete takes up. One study found a mix with about 30% in GGBS was optimal for carbon capture. And using those byproducts is good anyway, right? This is good anyway, right? Diverts waste.
So it could potentially be part of a carbon solution, not just less of a problem.
Well, it's an active area of research, but yeah, the potential is there. And overall, when you look at the whole life cycle, especially for things like repairing existing structures, studies suggest UHPC solutions can actually have a lower total environmental impact than doing conventional repairs, even with that higher initial CO2 per cubic meter. It's complex, but the long-term benefits are really key to its sustainability case.
Okay, let's try and wrap this up then. We've taken a deep dive into ultra-high-performance concrete. And it really seems to live up to the name, doesn't it? Incredible strength, durability, that surprising ductility, way beyond normal concrete.
Yeah, it's a material that lets engineers and architects achieve more with less material. Thinner, lighter structures, incredibly resilient infrastructure bridges, tunnels, and it opens the door for some really unique, complex architectural forms, too.
But, as we've discussed, getting it into mainstream use, well, there are some serious roadblocks. That cost difference compared to regular concrete is just huge, driven by those expensive materials and the tricky production.
Right. And there's still a need for more widely accepted design standards, more long-term performance data, and maybe most importantly, just getting more people, engineers, builders, skilled and comfortable working with it. That expertise gap needs closing.
Still, the research is pushing forward, trying to cut costs, find greener mixes, exploring things like 3D printing, even adding smart capabilities.
It really does feel like UHPC could be a significant step forward in how we build things. It offers answers for creating infrastructure that's not just strong, but resilient, long-lasting, and potentially more sustainable too, which is crucial given the challenges we face.
Which leads us to a final thought for you, the listener. We have this material, UHPC, with incredible performance and amazing long-term benefits, lasts longer, needs less fixing, uses material efficiently. But then we have these big upfront hurdles, the high costs, the complexity of actually using it wisely. So how do we bridge that gap? What needs to happen, do you think, to help this potentially revolutionary material move beyond niche products